What happens when a country loses access to the world's most advanced military supply chains, but refuses to stop operating the weapons it already has? For more than 4 decades, Iran has lived under varying degrees of sanctions, export controls, embargoes, and technological isolation. Yet something unexpected happened. Instead of simply abandoning aging American equipment, Iranian engineers began asking a different question. What if we cannot buy the replacement part? Can we build it ourselves? And what if the answer isn't limited to spare parts? What if captured technology can be studied, modified, copied, adapted, and eventually transformed into something new? Today, we're going inside one of the most fascinating and controversial stories in modern military technology. How Iran has used scarcity, captured equipment, reverse engineering, and battlefield adaptation to keep parts of its military functioning long after its original American supply chain disappeared. But there is an important distinction. Iran has not simply copied every American system it has encountered. Some Iranian claims are exaggerated. Some alleged copies are visually similar, but technically very different. And some capabilities remain impossible to verify from open sources. So today, we're separating the documented history from the military mythology, because the real story is actually more interesting. The military Iran inherited, Part 1, 1960s, 70s Iran. To understand Iranian reverse engineering, we have to go back before the Islamic Revolution. During the 1960s and 1970s, Iran under Shah Mohammad Reza Pahlavi became one of America's most important military partners in the Middle East. Iran purchased enormous quantities of Western military equipment, F-4 Phantom fighters, F-5 Tiger aircraft, and eventually one of the most sophisticated fighters in the American arsenal, the F-14 Tomcat. Iran purchased 79 F-14s in the 1970s. And that decision would have consequences decades later. Because after the 1979 revolution, the relationship between Washington and Tehran collapsed. The American military supply pipeline disappeared. Training and technical support were cut. Access to spare parts became extraordinarily difficult. And Iran suddenly faced a problem that every military planner understands. You can own the world's most sophisticated weapons, but if you cannot maintain them, sophistication becomes irrelevant. Imagine owning a fleet of aircraft, but having no reliable access to the engines. No guaranteed avionics supply, no official technical representatives, no factory support, no replacement components arriving on schedule. Iran had inherited the hardware, but it had lost the ecosystem that kept that hardware alive. And that forced transformation. Iran increasingly had to become not merely an operator of foreign weapons, but their maintainer, modifier, and sometimes manufacturer. The F-14 is perhaps the clearest example. The Tomcat was not designed to be an easy aircraft to maintain. It was a complex, carrier-based fighter built around sophisticated avionics, variable sweep wings, powerful engines, and most famously, the AWG-9 radar and AIM-54 Phoenix missile combination. The United States eventually retired the F-14 in 2006. Iran did not, and keeping Iranian Tomcats flying became a technological survival exercise. There is a common misconception that Iran simply reverse-engineered the entire F-14. The reality is much more complicated. Iran used a combination of maintenance expertise, cannibalization, local manufacturing, refurbishment, illicit procurement, and engineering adaptation. There is documented evidence that F-14 components reached Iran through illegal procurement networks. In 2007, for example, the Arms Control Association reported that U.S. military surplus F-14 parts had been purchased and diverted to Iran. Congressional investigations also highlighted the difficulty of preventing sensitive F-14 components from reaching Tehran. So the story wasn't simply, Iran copied the F-14. It was more like, Iran learned how to keep a foreign-designed ecosystem alive after the original ecosystem disappeared. And that distinction matters, because engineering isn't always about creating something completely new. Sometimes engineering is about solving an impossible maintenance problem with whatever resources are available. Component breaks, you don't have the factory replacement. So you study the component, determine what it actually does, determine what materials and tolerances are required, find a manufacturing process capable of reproducing it, test it, modify it, and eventually put it back into service. That is not necessarily glamorous, but militarily, it could be extremely valuable. And then Iran encountered something potentially even more valuable than a broken component: a nearly intact American aircraft. December 2011. Iran announced that it had captured an American RQ-170 Sentinel stealth reconnaissance drone. At first, Washington was cautious, but U.S. officials later acknowledged that Iran had indeed obtained an American RQ-170. CBS reported that a U.S. official had high confidence the aircraft displayed by Iran was the missing American drone. And this was not an ordinary drone. The RQ-170 had been developed for highly sensitive reconnaissance missions. Its stealthy flying wing configuration represented decades of American experience in low observable aircraft design. And suddenly, Iran had one. This is where the story gets controversial. Iran claimed it had penetrated the drone's systems, recovered information from it, and reverse engineered the aircraft. Iran subsequently unveiled aircraft it described as reverse engineered versions of the RQ-170. One example was the Shahed 171 Seamorg. Iranian officials publicly presented the aircraft as the result of reverse engineering. But here's where we need to activate truth mode. Did Iran reproduce the RQ-170 exactly? There is no strong public evidence proving that. Open source analysts have pointed out that although Iranian aircraft clearly resembled the Sentinel, resemblance does not establish that Iran reproduced the American aircraft's sensors, software, materials, manufacturing processes, or low observable performance. The War Zone, for example, assessed that Iran's claims of faithfully reproducing the RQ-170 should be treated skeptically, while acknowledging the significance of Iran obtaining access to the aircraft. And that's an important lesson. Reverse engineering is not photocopying. People hear reverse engineering. They often imagine an engineer simply taking apart a weapon and rebuilding it. Real reverse engineering is much harder. An engineer has to determine how was it manufactured, what materials were used, what tolerances are required, which components are commercially available, which components are custom, what software controls the system, how does the system respond to interference, how does it behave under heat, cold, vibration, electromagnetic stress, and most importantly, which parts actually matter to performance. A military system is not one technology, it's an ecosystem. Take a modern drone. The airframe is only one piece. There is the flight control system, navigation, communications, data links, sensors, power management, electronic warfare protection, ground control infrastructure, software, manufacturing processes, and the supply chain. Iran may be able to reproduce one component while remaining unable to reproduce another. That is why claims of Iran copied America's drone should be treated carefully. The more realistic description is, Iran obtained access to foreign technology, studied it, incorporated selected design concepts, and developed indigenous systems influenced by what it learned. That is a much more defensible statement. The RQ-170 wasn't the only American unmanned aircraft associated with Iran. Iran also announced that it had captured American ScanEagle drones. And unlike the enormous technological leap represented by the RQ-170, the ScanEagle was a much smaller reconnaissance platform. That made it especially interesting. Because smaller drones can be easier to reproduce, they require less sophisticated manufacturing infrastructure. They can use commercially available components, and they can be adapted for different missions. Iran subsequently displayed drones it said were based on captured American technology. The United States disputed aspects of Iranian claims, but the broader pattern was clear. Captured unmanned systems became an opportunity for technical intelligence. CBS reported in 2014 that Iran claimed to have captured several US drones and was copying the ScanEagle. But again, there's a difference between Iran copied the drone and Iran developed a drone influenced by the captured design. That distinction becomes crucial when evaluating Iranian military propaganda, because Tehran has an obvious incentive to exaggerate. Showing a visually similar aircraft can create the impression of technological parity, but visual similarity does not tell us what is inside the aircraft. Here is perhaps the most important part of the story. Iran's greatest advantage may not be any individual reverse-engineered weapon. It may be the engineering culture created by decades of constraint. Think about the difference between two military-industrial philosophies. The first says, if the component fails, replace it. The second says, if the component fails, figure out how to make another one. The second philosophy emerges naturally when supply chains are unreliable, and it can produce something extremely valuable: field adaptability. Iran has developed a military-industrial base capable of taking older platforms and modifying them for new missions. An aircraft designed decades ago can receive new avionics. A missile can receive a new guidance concept. A drone can be modified for reconnaissance. Another can be adapted for strike missions. A commercial component can sometimes replace an expensive military-specific component. Not every modification succeeds. Not every Iranian system is sophisticated. But quantity, adaptability, and affordability can compensate for technological limitations. And that philosophy is visible far beyond captured American equipment. It has become part of Iran's broader approach to missiles, drones, naval systems, air defenses, and unmanned warfare. Let's stop here, because there's a dangerous misconception surrounding this subject. Iranian reverse engineering does not mean Iran has somehow recreated the entire American defense industrial base. It hasn't. The United States maintains enormous advantages in areas such as advanced semiconductor manufacturing, aerospace materials, sensor technology, satellite infrastructure, high-end propulsion, stealth manufacturing, systems integration, and global logistics. A captured aircraft gives an engineer information. It doesn't automatically provide the factories required to reproduce everything inside it. This is especially important for stealth technology. A stealth aircraft isn't stealthy simply because its shape looks unusual. Its signature depends on geometry, materials, coatings, manufacturing precision, apertures, exhaust management, electromagnetic behavior, and mission-specific design. Reproducing the shape is one challenge. Reproducing the performance is another. That's why Iranian claims surrounding the RQ-170 should be viewed as both technically interesting and politically motivated. The truth lies somewhere between two extremes. Iran is neither technologically helpless, nor secretly capable of reproducing every American weapon it captures. The reality is much more nuanced. So why does all of this matter? Because modern warfare increasingly rewards adaptability. Imagine a conflict where one side possesses extremely sophisticated weapons but depends heavily on global supply chains. The other side possesses less sophisticated equipment, but has spent decades learning how to improvise. The first side may have superior technology, but the second side may have greater tolerance for attrition. And that's where Iran's strategy becomes interesting. Iran doesn't necessarily need to reproduce an American aircraft perfectly. It may only need to learn enough from it to improve its own systems. A captured sensor can reveal design principles. A captured drone can expose manufacturing choices. A recovered missile can reveal construction techniques. A surviving component can provide engineering data, and every piece of technology becomes a source of intelligence. This creates a feedback loop: capture, study, adapt, manufacture, deploy, learn, improve. That cycle is arguably more important than any single weapon. Iran's reverse engineering story is therefore not really about stealing American technology. It's about what happens when a military loses access to the industrial ecosystem that originally supported its weapons. The F-14 forced Iran to become a maintainer. Captured drones gave Iranian engineers access to foreign designs. Sanctions encouraged domestic production. And decades of battlefield experience created an institutional preference for systems that could be repaired, modified, and produced locally. Some Iranian claims are undoubtedly exaggerated. Some systems are far less capable than their American counterparts. But dismissing Iran's engineering adaptation entirely would be just as misleading. Because the country has demonstrated something militaries have understood for centuries. A weapon's value does not come only from how advanced it is when it leaves the factory. Its value also comes from what happens after it reaches the battlefield. Can you keep it running? Can you modify it? Can you replace what breaks? Can you produce enough of it? And can you adapt it faster than your opponent expects? For decades, Iran was expected to become increasingly dependent on foreign technology. Instead, isolation pushed parts of its defense industry in another direction. Not toward technological equality with the United States, but toward something different: independence through adaptation. The Iranian military-industrial story is therefore not simply America built it, Iran copied it. The real story is much more complicated. America built sophisticated systems. Iran acquired some of them. Iran studied them. Iran maintained others under extraordinary constraints. Some were modified, some were partially reproduced, and some became inspiration for entirely new weapons. That's the power and the limitation of reverse engineering. You don't necessarily recreate your opponent's entire technological advantage. Sometimes you simply learn enough from one captured machine to build the next generation of your own. If you want more deep dive analysis of military technology, weapons, strategy, and the confrontation shaping the modern battlefield, subscribe and turn on notifications. Because in modern warfare, the most dangerous technology isn't always the most advanced. Sometimes it's the technology an opponent has learned to adapt.